Okay, guys, so today we're going to talk about being a little more specific when we're describing covalent bonds. So, covalent bonds can actually be considered polar or nonpolar depending on the kinds of elements or which nonmetals are bonded together. So, in a nonpolar covalent bond, the electrons that are being shared equally because the nonmetals that are bonded to each other have either exactly the same or very similar electronegativities. So now, guys, you don't have the Regents reference tables to look up electronegativity. So we're going to be giving you a chart that has electronegativities for all of the elements, so that you can use numbers to figure this out. All right. So we're going to start off with this H2 molecule. And if I draw an H2 molecule, I have two hydrogens to stick together. So like there is no center molecule, it's just a center atom, right? And if I attach them with a single bond, each hydrogen has its valence shell filled with 2 electrons. So this is all that there is for a hydrogen molecule. Now, if we go to that chart I was telling you about and we look up the electronegativity value for hydrogen, each hydrogen atom has an electronegativity of 2.2. So that number tells you how strongly each hydrogen is pulling on these center electrons. So now, guys, you want to picture this as a tug of war. So this hydrogen is pulling on those electrons in that direction, and this hydrogen is pulling on them in that direction. Now, if you have a tug of war and both teams are exactly equal in their strength, the rope's not going to move. The rope's going to stay right in the center. And it's the same thing with those electrons that are being shared. They're being shared equally. They're right smack in the middle of both of those hydrogen atoms. They're not closer to one or the other because they're both pulling with the same strength. Okay? So that's how you tell if a bond is a nonpolar bond. We'll label that as a nonpolar bond, nonpolar covalent bond. So it's still covalent. We're just being a little more specific about how the electrons are being shared. Okay, so a polar covalent bond is the opposite. It's when the electrons are shared unequally because the nonmetals that are bonded together have different electronegativities. Okay, so let's draw HCl. So again, there's no center atom because I only have 2 atoms. So now I want to go ahead and give all of my atoms an octet. Hydrogen is filled up with 2 electrons, so that's good. I want to give chlorine an octet. Okay. I want to make sure that I did this right. So there should be 8 electrons in my picture. And if I add all of those up, there's 8 electrons in my picture. So I'm good. All right. So now, guys, if you look up the electronegativities of hydrogen versus chlorine, and you actually have this on your next slide. I forgot that this was in your notes, actually, because we're going to give you a separate chart that you're going to be able to use on like a quiz or a test. So it's showing us on this chart that hydrogen, it says 2.1. I know the reference table says 2.2. Either way, let's just use what's on this chart for now so you don't get confused. They're close enough. So hydrogen is 2.1, chlorine is 3.0. So again, guys, now picture this tug of war. Hydrogen is pulling that way on these shared electrons, and chlorine is pulling that way. But chlorine's attraction for electrons is stronger than hydrogen's. So if this is a tug of war, that rope is moving closer to chlorine. Those shared electrons are spending more time near chlorine. They're closer to chlorine's nucleus than to hydrogen's. Okay? So this is a polar covalent bond. They're not being shared equally. They're closer to chlorine. Okay, so how do we show that something is a polar covalent bond? You can see this 2 ways. Let me just change my color so that it's easy to see. Okay. So what we can do, guys, we didn't create ions here because nothing totally lost or totally gained an electron. It's just that they're being shared a little unevenly. So instead of making ions with full like +1 and -1 charges, we give these atoms partial charges. So because the electrons are closer to chlorine and electrons are negative, we say that chlorine is partially negative. That's a partial sign. And because of that, hydrogen is kind of or partially positive. So that's one way you can see a polar bond being labeled. The other thing that I've seen is we draw an arrow showing where the electrons are being attracted to more. So the electrons are being pulled towards chlorine harder. So we're drawing the arrow going to the right. And then we draw a little line there to show that hydrogen is the more positive side. Okay, so that's to show your polar covalent bond. So now this was the table I was talking about, guys, where we're giving you the electronegativities. I like this more of as like a visual for you guys to see on the periodic table where electronegativity is high. But we're going to give you a chart that you're going to be allowed to use on like quizzes and tests. Okay, so something that we didn't talk about, sorry, I skipped right over that. A dipole is created. So that means you have a molecule now that has charges. Like think about how a magnet has a positive and a negative end. So now we have these molecules that have a positive and a negative end. Okay, so another way of saying that is a dipole, two poles, a positive side and a negative side. Okay, so visualizing the dipole. So I kind of like this too on your note packet. It's not printed in color, but I like how this is in color. So in this first molecule, I have two fluorine atoms bonded together. So you can see that obviously those electrons in the middle are going to be shared evenly. So this is like a nonpolar bond. Where here we see the electron side. This is like our partially negative side, and this is our partially positive side in HF because fluorine is more electronegative than H, right? So it's a very big difference. That's a dipole as far as being a molecule goes. Now here we have LiF. So this is a metal and this is a nonmetal. So this is not a covalent compound. It's not really appropriate to call this a polar bond. This would be a polar bond here. This is actually an ionic bond. And you can see that the difference in charge is more drastic. So like lithium is not going to be partially positive. It's a +1 charge, a full +1 charge, where fluorine is a full -1 charge. It gained a whole electron. So you can see the difference in the charges there. Okay, so something that like the Regents likes to ask is like which compound has more ionic character, or they can say like which compound or which bond is more polar. So whether you're talking about ionic or covalent compounds, they could ask you this either way. They could give you only covalent compounds and say which one has more ionic character, even though none of them are ionic. All you have to worry about is being able to look up their electronegativities and find the difference of them. The more different the electronegativities are, the less equal the electrons are going to be shared and the more of a dipole you're going to have, or the more ionic character or the more polar you're going to be. Okay, so if we start here with fluorine, fluorine's electronegativity is 4.0. And difference means we subtract. Another fluorine also has a charge of 4.0. So what do we get as the difference? 0. So that's going to be our least polar molecule. It's going to have the least ionic character. For hydrogen and fluorine, again, fluorine is 4, hydrogen is 2.2 or 2.1. Whichever chart you're using, it might be slightly different. So there's a difference of 1.8. Okay. And then for lithium fluoride, again, fluorine is 4.0. If I look up lithium's electronegativity, it's 1.0. So the difference is 3. So see how LiF has the bigger difference? We know that LiF is going to have the most ionic character or be the most polar as far as the bond goes. Okay, so guys, in this box, there are some guidelines for you to go off of. If the difference is between 0 and 0.5, you can say that the bond is a non-polar covalent bond. So you can have two different nonmetals bond together. It doesn't have to be like two Fs. If the electronegativities are close enough, the electrons are still going to be shared equally. Between 0.5 and 1.7, we can call it a polar bond. Okay. And then 1.8 to 3.3 is an ionic bond. So now here's why I hate using these guidelines. I actually would prefer you guys to use the definitions of each type of bond first, and then use this if you're not sure. So HF is not an ionic bond. H is a nonmetal and F is a nonmetal. So I would never call HF an ionic compound, but I would say like it's very, very, very polar. So look at the types of elements first. Then once you decide ionic or covalent, then you can use your electronegativity differences to decide if the bonds are polar or non-polar as far as covalent goes. Okay. I don't love these numbers, but they do show up. So that's what I would prefer you guys to do. All right. So guys, if you can use that electronegativity chart, I'm going to have you calculate the electronegativity differences for these 4 molecules and then answer some questions about them. Okay. Have a good one.